So then we'll go to the next step in this session with a presentation of Lorie Hamelin, with heading a chair, junior chair, professor, and not junior, professor chair. So it's so in Toulouse, and so on sustainable transition towards fossil carbon. And I am very happy to have Lorie here because she's a very busy woman, so international reputation and very strong knowledge on all this integrated approach of LCA and all is related with transition, etc. And I will leave you the floor. Thank you.
Thank you. Merci Bernard. Merci Romain. So good afternoon, everyone, and thanks for having me. So I'll try, yes. So as Bernard said, I'm a professor holding an INRAE chair on sustainable transitions towards low fossil carbon economy. I removed the word junior. And then it's based at a lab called TBI, that stands for Toulouse Biotechnology Institute. It's based in Toulouse, as the name says, and it's part of the Federal University of Toulouse. And today I'm going to talk to you about a topic that I'm really passionate about, and it's these sustainable transitions towards low fossil carbon economy, so the challenges and prospects toward that. And just before I go to my next slide, I need to say that I'm also a life cycle assessment practitioner, so I analyze systems and product in a holistic way, so from the extraction all the way to the end of life. And I also look not only at carbon, so I would say a lot of carbon today, but it's not only that. It's also all flows, and then the trade-off between climate change or global warming, we don't know what to say now, and the other impacts. So the first part of the title, the transition. If we say that we want to do everything we do today, so to supply all the products and services in the economy without fossil carbon, so that is without natural gas, without coal, without oil, what does that mean? How can we do that? Well, first thing we can do, of course, is to do without carbon, and that's very smart to do that. So that is the so-called decarbonization. And this is possible essentially for electricity and all the services that you can supply with electricity, like heat, and like some type of transportation. I mean, even today we can fly planes on battery. Whoops. So that's one thing we can do, and that's good, but we still need to eat. We still need materials, as we just talked. We still need chemicals. So where do we get the carbon from? One thing we can do is from biomass, so that's the most accessible, whether it's from land-dependent biomass or residues. Another thing we can do is to take it from the atmosphere, suck it up and concentrate it from the atmosphere. That's the so-called direct air carbon capture. We can also do that. It's just, let's say, less accessible than biomass, but it exists. And we can recycle carbon. So once we have the carbon, we have all our interest to keep it in what we call the technosphere as long as possible. So reuse it, try to capture, use, and transfer back, and capture and use and transfer back. So what is important to remember is that in a low fossil carbon economy, carbon becomes a limited resource. So we have to use this as efficiently as we can. So in the title of my presentation, there was a challenge and prospects. So that's a bit the prospects or the messages for the students in the room and the future CEO of companies or startup funders or policymakers. So one message, don't waste biomass carbon on services that can be supplied without carbon. That's a stupid thing to do. So if you can electrify, do it. Second message, help us creating solutions using carbon as efficiently as possible. So more of the carbon should go to the service and less should go to the unrecoverable or hard to recover carbon. Third message, help us with solutions to recycle carbon as much as possible. And another message, it's not about carbon. So we talk a lot about decarbonization or solutions with low carbon. It's not carbon the problem, it's about fossil carbon. So I like to say, stop this decarbonization nonsense. We need carbon, it's essential on life on Earth. Now you can ask me, okay, Lorie, but why do you want to do this? Why do you want to supply everything we do today in society without fossil carbon? And part of the answer lies in the Paris Agreement, which I like to represent as a very delicate balance. So I've put the yoga, I don't remember how that position is called, but there is these three pillars. So on the one hand, we need to do greenhouse gas mitigation. So that is to supply a given product and service. We need to do it with less emissions than what we do today. So that's mitigation. We also need to keep fossil carbon in the ground. So that's our substitution, where we want to instead use biogenic carbon or other type of carbon, but not the fossil one. But that is likely not to be enough to reach this balance. So we also need to have removal, and that's the so-called negative emission. And then we also need to have these biophysical removal, so additional removal of carbon from the atmosphere, for instance, to the soil. We talk about balance, and whenever you do these life cycle assessments, so this graph is without importance here, but it's important to remember that what we're trying to do, we have a process, we convert something, it's going to have impact, we're going to need electricity, we're going to need a lot of reactants, and there are impacts associated to those, climate and other impact. So this is the bar you can see there, these are the impact. But then you want to replace something. So let's say that you're doing a new protein, and then you want to replace the protein that we consume today, let's say soy. So avoiding the soy is what you have here in the avoided and in the negative impact. And what you want to do is that when you do this minus this, you want to be below this zero bar here. So you want to be like this type of system and not here. Otherwise, well, you're not doing any better. So that's also kind of basic, but we often forget this because we go very deep in our process and we forget the basics. So I was talking about challenges in my title, and one key challenge is the land, or here I called it constrained resources, mixing land and waste in parentheses. One thing we know about land is that it's limited. So we have 12.5 gigahectare of land area on Earth. And then this morning we saw with François that it's not getting any greater. It's quite the opposite. We have 4.5 gigahectare of agricultural land. So 1.4 is arable land where we grow our crops. That's about the size of South America. And we have 3.1 gigahectare of pasture. That's where a cow or the sheep are grazing, and that's about the size of Africa. We also have 4.9 gigahectare of forest, so kind of a similar area. And we have 3.1 gigahectare of land that basically cannot be cultivated. What's important here to stress is that we are already using about a little more than a quarter of the available arable or agricultural land just to grow, we are already using 1/4 of the land just to grow food and a little more of that. So if we want to use more of it because we want to grow biomass for our bioeconomy, then we can ask ourselves, well, where is that going to come from? And then most likely we are going to take up from this forest area. So that leads us to the so-called land use change. Sometimes you can say some are direct or indirect, just to illustrate it very quickly what that is. So say that you want a bioeconomic crop in France, let's say miscanthus, or it could be hemp. Most likely that's going to be grown on arable land. And then very often in Europe we have ambitions to preserve the forest area we have. So if we want more arable land to grow it, then it means that something else that is already grown on arable land is going to be kicked off. That's why I have it in a dotted line. This was a case for Denmark. We could see in the statistics that it was typically barley. So barley is kicked off, you grow, say, your miscanthus, you have some effects associated to that, and that's often called a direct land use change. And that would be, very often in this case at least, it would be positive because you would have more soil carbon sequestration, for instance. However, this barley that you no longer produce here in France is still demanded on the market. So how is that going to be supplied? There's two key reactions. One is that somewhere in the world, because there's going to be a price effect, so farmers are going to be tempted to boost their yield, maybe to have more fertilizer per hectare. There's different ways to do it, but to grow more out of the same hectare of land, that's called intensification, but that also comes with an environmental cost. And another way is that somewhere in the world, nature is going to be, let's say, cut and transformed to arable land. So that's the deforestation. And that also comes with a huge carbon cost. So this effect here, often called the indirect land use change, has an impact of, well, we quantified it between 4 to 5 kilogram of CO2 equivalent per hectare. And that's about the same, ton of CO2 equivalent per hectare. And that's about the same as, let's say, 1.5 car per year. So two messages here. Does your solution demand extra land? The moment the answer is yes, it implies a share of deforestation and intensification and emissions that goes with it. And message 5, on the other hand, if you have a solution that can prevent the additional demand for land, so if, for instance, if you have a new food production, then this can lead to important greenhouse gas saving. And now we have the case of the so-called residual resources. Our friends in the biotech, they like sugar a lot, and then they are happy often to say that they are going to use sugar beet molasses, so that has no impact because it's a residue from another industry that produces sugar. Yes, but, and this is what we need to remember, if before you mobilized it for your process, you need to look what was happening to it. And then in this case, it's already mobilized for animal feed. So it would have been used for animal feed, so it's no longer used for that because you mobilize it. So the nutrition it was providing to animals no longer happens. So then you need to compensate and grow that carbohydrates that your animal needs somewhere else. And that leads to the so-called land use change effect that we were talking earlier. So this has an effect on climate, but also marine eutrophication, acidification, and water scarcity, typically. So no free lunch is the message here. So message 6, always consider what was done with the resource before you mobilized it. The power fluctuating, or I should say power challenge. So why is that important? It's because very often, you know, in this positive bar of impact I was showing you, electricity has a large share, very large share of it. And here we have the, let's say, the opportunities we can have with fluctuating power. So we have a case that was a paper we did for Denmark, but it could be applied anywhere, where you have in the x-axis all the 8,000 something hours of the year, and then in the y-axis you have the power. In black you have the fluctuating power, so that's, in this case it was the sun and the wind, and in blue you have the electricity consumption, the demand. And the way the power system is built today is that you always need to match what you produce to the demand. If you don't do that, then you're going, or if you supply too much, you have a breakdown in your equipment. If you supply too little, well, you just have shutdown. So, and then there is, in every European countries, there is a TSO, technical system operator, that is in charge to regulate that. And what's important and interesting to note is that, okay, this is the 2017 projection with a certain capacity of fluctuating power installed. And this is a 2035 with much more, nearly tripling, or doubling, sorry. And what we can see is two things. One thing is that we have this hole here. So it means that if you have a technology like incineration of biomass, you are running continuously here, and you produce constantly the same amount. But that's stupid because it means that in some hours, like here, you compete with the wind. And as I said earlier, I mean, now we know the cost of biomass. So it's very stupid to burn or to use this biomass when we have wind available anyway. So we should produce it just in these hours in white. And that is something we can do with technologies like biogas, for instance, because we can gasify our biomass, then we store it in the gas grid, and then we can use it just here when there is no wind. And the second thing we can notice, and that's something we talk a lot about, so if we go, well, yeah, in this system here, first of all, there's still these white spots. So that means that in the hours that there is no wind and sun today, there's going to be also no wind and sun in the future, makes sense? But we also have a lot of these peaks here. And that is these hours where we are producing more fluctuating than the actual classic consumption. And this is where we are very interested, or we should, in our bioeconomy. And you hear a lot about it. Oh, we're going to use that and feed it to an electrolyzer, split water into hydrogen and oxygen, and then use this hydrogen for bioeconomy. Of course, sometimes it might seem idealistic. It's not impossible, but anyway, it's an opportunity. So message 7, don't kill an idea just because it needs a certain quantity of power. So it may not be an issue in the future, and we cannot exclude electrifying heat. That's something important to remember. And message 8, renewable gas is not just a source of power, but also of hydrocarbons. So you can, that's what is really interesting about biogas. You can use it for whatever you like. It's a very simple molecule, CH4. And that also gives it a lot of flexibility. Very quickly on nutrients, because I know that there's going to be a talk about it afterwards. But it's very important to remember where we get our nitrogen and phosphorus from. So nitrogen, many people forget it, but the way we produce it today is through the Haber-Bosch process. So we take nitrogen from the atmosphere, and then we couple it, we want to make ammonia. So the hydrogen is coming from natural gas that we are cracking. So that has a lot of emission, and it makes us very dependent upon natural gas and country producing this natural gas. So, and the other problem is that we have anyway way too much reactive nitrogen in the technosphere. I mean, that's what we do. We take this nitrogen from the atmosphere and put it in the technosphere. So we have all interest to instead recycle our nitrogen much better. And that the same apply for phosphorus for different reasons. So here it's because we have limited physical reserves. And that's also a very important nutriment because it's simply, you cannot replace it. And then you know the so-called planetary boundary framework, and you can see that both the phosphorus-nitrogen boundaries are way exceeded. But I won't say too much more on it, just a little message. Recovering nutrients makes a lot of sense. Also to decouple nitrogen from natural gas. I put it in parentheses with François talk, but okay. And ensure security of supply. Well, in a world where everyone is responsible for everyone, maybe that's not an issue. For nitrogen, can you do it at a lower environmental cost than Haber-Bosch? Yeah, so you need to do better than the current process. For France, so we asked ourselves that question, can we build a sustainable roadmap towards low fossil carbon economy in France? And that's a project that was financed in the framework of the so-called Make Our Planet Great Again initiative of President Macron. And here what we did, and I won't go through everything we did, but just highlight a few things. So we had 6 research objectives. The first one, and we focus here on the residual biomass. So the first one was to understand, okay, what kind of residual biomass do we have available in France? Where do we have it? How much do we have? And importantly, what are we already doing with that? So whatever we do with this was the second research objective, we should perform better than this use that we are already having with it. So in this second research objective, and I'm just going to show you a few results, we look at several ways to use this biomass to produce different products and services. So for instance, ingredients for animal feed or human even food. We also looked at, okay, the production of gas, production of oil, production of aviation service. And we looked at different technology to do that. And then the idea was to figure out at the end, at the scale of France, which of our residues we should allocate to which technology to produce which product and services in order to optimize the overall environmental performance. And I'm going to talk about this research pillar as well, because that's one I really like. And this is about crop residues. So that's a very important stream in France. In terms of petajoule, it represents more than 55% of what we have. So we have a lot. It's dry matter, it's great. But the only problem is that we often say that we shouldn't take more than some 30% of these crop residues from our soils, because it's going to deplete the amount of soil organic carbon stocks in the long term. But then we thought, aren't we depriving ourselves from a very useful resource for the bioeconomy? And what about if there is an interaction between the way you use the straw, because you convert it, for instance, to bio-oil through pyrolysis, but there is also a residue, the biochar, that you can return back to land. And if you consider that, couldn't it be possible that you can take more straw than you thought without affecting the soil carbon stocks? So that's, I'm going to show you some result of that. And yes, I'm going to go straight to that. I went too fast. So these are the results of that objective I was telling you in this interaction between bioeconomy and how much straw you can take. And what we could see in our result is that when we compared, okay, in one case you leave the straw on land and we looked at that over 100 years. And in the other case, you will harvest the straw, you transform it in different bioeconomy pathway, and you return the co-product. And what we figured is that after 100 years, all over France, because it was a specially explicit modelization, we would have no soil organic carbon losses at all if we return the biochar back. And not only don't we have any loss, but we even increase the stock, because this fraction is more recalcitrant. For gas char, so the sort of char residue you get from biomass gasification, we had very similar results, so no loss all over France, and some increases, but not as important. For hydrochar, which is the residue you get from hydrothermal liquefaction, where you also produce a bio-oil, we also observed that we had, in general, increases. And then we had some minor loss, you could see here in the north. And for digestate, it was 50-50. So we didn't really have an increase, but not really much a decrease either. And then we looked at it for molasses when we do bioethanol, and we returned the molasses fraction back to the soil, and that after separation, so the dry fraction was burned, and then we considered that the liquid fraction was returned back to soil, and here we would have an overall loss of soil organic carbon stock. So that was an interesting story. Of course, it doesn't tell everything, because here we don't have the complete balance, and that's something we're going to do later. Okay, what is the balance when you consider what you actually do with the oil, what you actually do with the gas? But we can say that if maintaining soil organic carbon stock is our only concern, we have much more biomass potential than we think, and there's no need to lose 170 to 225 petajoule a year to atmosphere, which is the gross electricity production of Greece and Austria combined, so it's not negligible. And I should only say that this is a result we got with colleagues also from the unit here at Reims. So, 10 message, leaving a biomass on land is no magic for soil organic carbon enhancement. So most of the carbon is going to be lost as CO2 to the atmosphere when we talk about crop residue. But of course, organic matter input does bring a magic to the soil. We know it's good. We're just not that good to quantify the long-term, let's say, implication in quantitative terms. Also, we're not that good to understand the long-term effect of biochar, just because we don't have that much open field experiment. The most we have is some 8 years. So there's still a lot to understand here. Digestate, on the other hand, would not bring negative emission, so we don't have an enhancement. But on the other hand, it may be considered safer because the structure of the product is not changed, so it's not like thermochemical conversion. And losses that we observe there could be avoided by combining with other strategies of carbon return, like cover crops. This is part of a PhD defense that will be defended 23rd of June, and also online if some of you are interested. Then some results about this waste to nutrition. So using residues and then convert them with different pathways. So here we considered 11 streams. We considered their biochemical composition. Then we considered 27 biomass management pathways, so 15 waste to nutrition pathways, including insects, microbial proteins, among the most popular. We considered what we call the counterfactual, so what would have happened with it, decay on land, for example, or heat, and some other alternative like anaerobic digestion and gasification. There's different process parameter, emission parameter, and we took the range and varied these. So in total, 293 parameters and variants were considered. We did the LCAs and got some results. I've put that just as provocation for those that have seen that. And one thing that we found is that the only way that feed-grade residual streams provide more environmental benefit than direct feeding to livestock is to produce ingredients substituting meat production. But that was only true under very specific conditions, so where we had the maximum conversion yield, where we had a completely decarbonized electricity, and then when we had a complete meat substitution, because in kilogram, we just looked in kilogram equivalent, because we don't really know what's going to happen. If 1 kilogram of insect replace 1 kilogram of meat, well, that is to be figured out. Yes, so in this case, this was only possible with mycoprotein and insects. Then another message that was very important here was how good or bad the alternative is. So here it's our marginal protein. So we had these different conversions mainly to provide protein. And the marginal protein, well, soy basically. How good is that? Because what we figured out is that today, it's about 4.5 kilogram of CO2 equivalent per kilogram dry matter for soy production. If we are doing, if the impact of our protein that we are producing is below 4, then we figured out that there is no value of doing this waste to nutrition. There's just no gain. However, if we are in a future where the production of this protein has a much higher impact because we have a bad governance, there's more deforestation associated to it, the yield is not as important as it is now, then it could make sense. So if we are above 5, then microbial protein was one solution that could make sense. So what you compare it to and how good or bad it is also something very important to figure out if it's worth doing it. And then another thing that is important is to remember, is this solution rather adaptation or mitigation? And we figured out with these waste to nutrition, so do we want to end up eating wood and, and straw through different transformation? Well, we figured out that environmentally speaking, at least, it's more an adaptation strategy. So it only makes sense if under a prevailing failing global governance. Another result, very quickly, so this was about aviation of the future, where we compared biofuels, electrofuels, different types of battery and hydrogen to fly people over, in this case, it was the near-term domestic 6 trillions of revenue passenger kilometer a year. And it was very interesting to see that the biofuels, they could be very interesting, but that was providing that we are using primary forestry residues and that these residues would have been left to decay on land. And then the problem we realized there is that this blue part here is essentially due to methane emissions from that. And you could think, how come is there methane emission? Well, it could make sense because you have a forest floor and it accumulates, and then there could be some anaerobic zones where methane is created. The only problem is that we don't have very good values, and no one has done a lot of tests, again, in the open air. So we use what we could find in the literature. First, it was a factor of 10% of the carbon from the biomass emitting as methane. And yeah, that was way too high. This now we reduced it to 3, where we found value varying between 0 and 10. And we really don't know, but if it's 0, this whole blue part disappears. So we realized, well, that's a very sensitive parameter. And then what we figured is that in general, well, the electric system looked very interesting. But of course, that only applies for the domestic case. And then you can think, well, why not doing it by train then? And the hydrogen, otherwise, was often the one, the lowest. There's much more to go in depth of these results, and that's a PhD thesis that's going to be, it has been defended, it's going to be online soon. So where do we go from here? What we want to do now is to do this optimization I was talking about at the scale of France, but really looking at reconciliating both the supply, let's say, the resources we have, and the demand, so where to allocate it. Also, something we are doing, so that's part of the next steps, looking at strategies involving cover crop. And then one thing also that I think combines very well with what we heard this morning is that, okay, now we have these LCAs, but are they very useful for decision making? We provide all the trade-offs, but is that something that speaks to our public policy makers or to the stakeholder taking a decision on bioeconomy? And this is here, yeah, what we think is needed to make this whole technological project as an actual societal project where solutions are implemented. So we want to understand better what perhaps KPIs or what indicators could be more useful for the stakeholders. So some take-home messages, I already put them through, so I will go very fast. We are allowed to think beyond the current constraints. So for instance, it's not because something is not allowed today that it cannot be done in the future. So don't allow yourself to be creative, let's say. But it must make sense. So we can do many things technically. That's what I show with the waste to nutrition. But it doesn't mean, sorry, that it makes sense to prioritize the biomass resource and time and effort and money for this solution. And yeah, I've put that because I think it's important to remind very often colleagues, people think transport is going to be very important. But in our LCA models, because you don't transport one apple or one gram of straw, it ends up to not be that important. Okay, if you want to know more, some of our publication. And on this, well, I would like to thank you for your attention, and I hope there's many questions. And time.
So, is there any question? Or many questions? It's better. Yeah.
Thank you. Could you tell a bit more about what is waste to nutrition? How is it transformed? What does it give rise to?
Yeah, I can try. Of course, my PhD student, oh, I also forgot to say, he has a PhD defense on the 12th of April. That was not this one. So, yeah, well, the idea is to convert residual biomass into ingredients. So, for example, I can think of one technology now. I don't have all numbers in head, but Arbium, perhaps you've heard. So here you take wood, or it could be wood residues, and you will convert that to sugars. And then these sugars you will use in fermentation to produce mycoprotein. And then that protein is going to be, well, what you can sell to the market. That's one example. You have the green biorefinery, where you want to get the rubisco, basically, and the green protein. So you will have grass or whatever biomass that produce something green, let's say. You press it, and then you will get a juice that you then can further process to get a protein concentrate. And then you will get fibrous biomass that can be returned for cow or ruminants. That's another example. I don't know if it answered the question. I could continue with the different... Oh, yeah. Insects is another one, yes. So in the case of insects farming is that you are going to supply, for instance, food waste to feed some larvae that will then grow, and then you will, of course, make a sort of meal out of it.
Okay, another question. So I have one. It's two. Okay. Who asked? Okay, I'll come back.
Hello, it's just a simple question. Do you work on urban waste to nutrition? Like the valuation of urban waste? Bio waste, I mean.
It depends what is urban waste. We tried our best to have greenery cuttings, for instance, that we try to capture. And I don't know if you count, no, agri-industrial waste doesn't count as urban waste. So we have in the woody residual biomass, we have captured the urban management of parks and grass. That's the only thing we have.
Yes, thank you very much for this really interesting talk. And I don't come from this field, so if I use words wrongly, please tell me how I should use them. But some also political debates about this has to do, for instance, when we speak about some heating and so by using residues for woods. As I understand, you can have the same technology to use using some residuals, or you take just the wood and you cut the tree. And my question is, are these technologies which are somehow neutral? For instance, what you use in this technology, what kind of wood? Or do we need much more also discussion about the technology which could have this kind of dual use? So for instance, or does the same technology can support deforestation or the use of residual wood, for instance? I don't know if you understand the question.
I can try to reformulate and you tell me if I understand.
Oh yeah, this will be great, thanks.
But if I understand correctly, the question is on the flexibility of technologies, so those that can provide more than one service?
Or if the same technology can actually have a positive impact, for instance, by using some residues, or can contribute to deforestation. So.
You mean if I can supply it feedstock that would come from land dependent, let's say, or?
Oh, it's more the question about the technology which is used. If we can talk about dual use technology, which the same kind of technology can be used to reduce the use of fossil, but if you, for instance, cut down a tree to make out of it biofuels, I don't think it's what we want to do.
I'm not sure I understand.
Okay, no problem. I will ask you later.
Sorry.
Je crois que c'est le procédé de transformation en fait. Comment tu utilises les procédés de transformation s'ils sont génériques ou pas?
If the transformation are generic or not, but I'm not sure.
We are on the same institute, so maybe just if I understand, it's how you have generic transformation systems to produce or food or chemicals or other things like that. Okay, so maybe you can discuss that.
Sorry.
Okay.
No, I just thought the question was whether the impact could differ depending on how you source the raw materials. So whether it is residues or whether you actually take it from a forest. I think that was the question. So if you use wood that you cut from a forest, or if you use wood residues for parks or things like that.
Okay. I mean, maybe that's linked to the so-called rebound effect. And then, of course, that was another slide. I didn't talk about it, but you can base a solution on the waste, and that sounds great. I mean, that's a bit what I presented with the sugar beet molasses. But if you're very serious about it, then you're not going to have enough at some point. What's going to react then could be your tree from the forest. And this is something we have to be, of course, very careful about to prevent or not investing. For instance, because that's what we have to remember, our investments, they are going to be there. I mean, there is a payback time. They are going to be there for at least some 30 years. So if you invest in producing bioethanol from straw, but it means you're going to you're going to need straw or something to put in for at least the next 30, 40 years. And if you run out of straw because there's a dry year, climate change, or because, you need it to feed the cattle, what do I know? Or there's other contracts elsewhere, then you don't have it. You need to supply the lignocellulosic biomass, and then what reacts? Then it could be a rainforest from Brazil, and that's not what we want. So indeed, that's something we have, that's why in LCA we have something called consequential assessment, where we try to capture this effect and really take the supplier that would react to a demand change to anticipate this rebound effect. Yeah, it's very important indeed.
Yeah, but I think we don't have so much time for another question because we kind of delayed. I will ask Lorie afterwards. So we're going to do a small break of 15-20 minutes, like this. We're not too late on time, and then we carry on with Tanguy. Is that okay?
So thank you, Lorie.